Assalamualaikum warahmatullahi wabarakatuh and hi. So for this week lecture video, in week 4, we're going to continue what we have seen last week. We are still in the second topic of mechanical energy conversion principle. And we're going to look at the second method of calculating the electromechanical energy conversion. So basically calculating either the torque or basically or the power that is produced in mechanical in mechanical part. We will basically look at the force and torque. So last week we have started with the first method, which is by using the principle of Lorentz law, right? So we calculate the force and then calculate the torque from the force, and the force is basically by using the equations of Lorentz law that says that the force is proportional to, of course, the first one is the intensity of the magnetic field or flux density B, and it's also proportional to the current that is circulated in the conductor I, and then proportional, of course, to the length of the conductor that is placed inside the magnetic field. So the equation is basically it's a vector product, a cross product of B and I. So it's BI multiplied B multiplied by I multiplied by the length L sinus theta. So theta was basically the angle between the magnetic field and the direction of current that is circulating inside the coil. But this week we're going to look at a different method, because in electrical machine it will not always be as easy as what we have seen, where we have consistent magnetic field which is regular and uniform throughout the surface, the area, and then we will not always have only one conductor. So it's going to be quickly becomes very complex. So what we're going to do today is basically using what we call as the energy method, using energy method, by basically understanding that in order to produce the mechanical energy, the energy has to come first from electrical energy, and then it is conserved inside the machine in the form of field energy or magnetic energy, and then later convert into mechanical energy. So we're going to try to look at that method today, and it is basically the usual method that we are going to use in calculating the force or basically the torque that is produced by an electrical machine. So let's begin. Very quickly on the revision a bit on what we have seen last week. Last week we used the first method because there are two methods that we're going to look at. The first method is basically the basic principle method that was in the exercise we have seen last week. It was applied to what we call as an elementary form of a DC machine, where we have basically this is the rotor, or what we call in DC machine later, if you look particularly in the topic of DC motor or a machine with commutators, we have the rotor, which we call armature. And then we have in simplistic form or elementary form, we have two conductors, right? So the conductors, we have current circulating inside the conductor. So here are two conductors, and the rotor or the armature is placed in constant magnetic field B, like this, right? So in this form, which is very elementary and simple, we can basically use the Lorentz law that says that the force produced on the conductors equals to the cross product or vector product of the current with the magnetic field. So it's basically the current I. So J is basically the what we call as current density. In other terms, is basically just current inside the conductor. If you multiply it by the surface area of the conductor, you can consider it by as current I multiplied by the magnetic field. And this is, of course, is a formula for in the form of density at one point. So if you want it to be applied through the whole conductor, we have to multiply with the length L. So it's basically I, B, L, and then it's a vector product, a cross product. So there is sinus theta. Theta is the angle between these two fields, current and two vector, current and vector of magnetic field, sinus theta, right? So we get the force on one particular conductor. So it is applicable for this case, in which case we only have two conductor. You can do it, but imagine if we have multiple conductor and the form of magnetic field are not as consistent as in this DC machine. So what we're going to do is basically we're gonna need to use a different method that is more generic and take in the form of basically accounting for the energy transformation of energy rather than calculating specifically the force at each particular conductor. So this method is what we call as the method of force calculation using the energy method. So we will not, there will be no Lorentz equation or detailed equation on the basically the creation of force from the magnetic field, the interaction of magnetic field and the current inside a conductor. If we look in the equation later, the equation is more or less talking about energy rather than particularly current and magnetic field. So what we can see is basically when we talk about energy, we can imagine if we have our system of electrical machine, which we can call in generic form as a lossless magnetic energy storage system, right? So that's what it is. It converts basically electrical energy into mechanical energy via what we call a magnetic medium. So we can basically simplify it in this schematic diagram. We have in input a certain current I and a certain potential difference E, right? The electrical terminal. It gets into our electrical machine. It is basically a lossless magnetic energy storage system. So it stores the energy in the form of magnetic field. And then if we need to consume it in the form of mechanical energy, it will create a certain force, or later from force we could certainly calculate torque. The force here is have an annotation of force field because it is a force created by magnetic field. So this is in the form of schematic diagram, but in reality what happened is basically we are supplying our current and our voltages across a certain coil, across a certain what we call a winding, right? So in the winding we have a certain inductance due to the coil and the magnetic circuit. And then we have, of course, in a coil, you cannot have a completely perfect conductor. So there will be a certain small value of resistance. So they will be accounted as the small winding resistance. And the magnetic core, in which will circulate the magnetic flux, will have basically a certain air gap with an element that will be a movable element. So in this simplistic form, we're presenting it as a movable magnetic plunger which can move laterally in function of the magnetic flux that is circulating inside the magnetic core, right? But in reality, in electrical machine, it's going to be a rotating machine. So this air gap is basically between what we call the stator and the rotor, and the rotor doesn't have a lateral movement. It's going to have a rotational movement. So if we look here, an example of like electromechanical energy conversion device, this is the most simplistic form, which is a magnetic plunger. What is magnetic plunger? Is basically we have this element which is made of a same ferromagnetic material as the core over here, and we can move it. As it moves, basically what happened is we change the value of air gap, therefore the value of reluctance, right? So if we change the value of reluctance, then the magnetic flux phi will also change. Therefore what we can, if later we calculate the inductance, we know the inductance is basically is inductance L is the value of flux linkage, which is the number of coil N multiplied by the flux divided by the current I will change. So in function of the position of this plunger, the inductance of the system will also change. So in function of that variation of value of inductance, basically we will create a certain force on the plunger, either to attract it to become aligned. We will attract it to become aligned with the core material. So the input for the system to attract this movable magnetic plunger is basically the electrical energy. So the input is basically current I and voltage E, and the mechanical output is when the plunger is moved due to the magnetic attraction due to the variation of reluctance, because of course our magnetic field want to always reduce the reluctance, right? So the force that attract or move this plunger is we're going to call it as a force field, F, a field, right? So the conversion is considered without losses. What does it mean without losses? It means all the energy that is coming from the electrical energy will be able to be converted into mechanical energy to move the plunger. Okay. So the interaction between electric and mechanical occurs through this medium of magnetic field of magnetic circuit, through the medium of magnetic circuit. So in this medium of magnetic circuit, basically the energy, we call it as the energy is stored in the form of magnetic energy inside the core. So it is just the medium in which the energy travel through from electrical to become mechanical. So here the energy is somehow stored to convert the electrical into mechanical. So without losses, the stored power in the magnetic field can be written as this equation. So what do we have in this equation? Basically, on the left hand side is what we have transformed into mechanical energy. So here is the energy of field, W energy or work. So if it's a movement, then we call it as work, right? So the work divided by time, this is basically power, right? Because power is the amount of energy or the amount of work per over time. So this is what we call as the mechanical power. So mechanical power produced by the movement of the plunger equals to, so here EI, you know what it is basically the power in the form of electrical energy. So electrical energy is basically the energy that is absorbed from the electrical part in the winding, right? Minus the force field multiplied by dx over dt. So force multiplied by dx over dt is basically the distance in which the plunger moves. So this is basically the energy the energy produced in the mechanical form. Okay. Let me re-clarify it a bit. So this is the energy in electrical, EI, minus the energy in mechanical. FLD is the force here multiplied by dx dt, therefore is the dx is the distance, so force multiplied by distance is the energy or the work done in mechanical divided by time, therefore is power in mechanical. So here is the energy input in electrical, right? Here minus the energy output in mechanical. So here over here, sorry, just now I explained to you this is the mechanical energy. So this is not the mechanical energy. So the energy here is the subtraction of input over output. So this is basically the energy that is stored in the magnetic circuit. So W field is the energy of magnetic field divided by dt. Therefore, this is the power of magnetic field. So the power produced by the magnetic field or the energy stored in the magnetic field is basically the subtraction of the energy input over the energy outputs, because we know the input is the electrical and it will be converted into magnetic storage and then mechanical. So if we deduct the input with the output, we get the energy storage in magnetic form. So the power in the field, the power of the magnetic field equals to the power of electrical minus the power of produced in mechanical. So if we can quantify, therefore, if we want to calculate the energy stored in magnetic form, if we know the energy that is absorbed by the system and we can monitor the energy that is produced in mechanical form, therefore we can deduce the energy that is stored in the magnetic form. So without losses, the stored power energy takes the form that we mentioned just now, right? So the energy in magnetic field equals to the energy input in mechanical minus the energy output in electrical, minus the energy output in mechanical. So knowing from the second week's lecture of Faraday's law, we know that across the winding, there is a variation of flux, right? So E, which is the voltage supply, if we look at it in terms of a generator, if we produce a certain movement in mechanical, we could obtain a certain voltage or potential difference, and that potential difference E is equals to the variation of magnetic flux linkage d lambda. So lambda is just n multiplied by phi, n multiplied by the magnetic flux, right? So it is what we call flux linkage. So the voltage is basically d lambda or d phi multiplied by n divided by dt. Therefore, we can also rewrite the equation on top over here if we replace E with d lambda over dt and multiply everything by dt. So to account for energy and not power, we will get basically d omega field, d W field, so the amount of energy in the magnetic field equals to the current. So now I'm replacing E with d lambda over dt, right? So I'm getting I d lambda when we multiply everything, all the equation with dt. So it equals to I d lambda minus, so here we get the energy in mechanical form, force field, mechanical force of the field multiplied by the distance traveled by the plunger, right? So we get this equation, and this equation is basically the equation what we call the equation that form the basis of the energy method. Okay, so energy of the magnetic field storage equals to the current multiplied by the flux linkage minus the energy produced in mechanical. So without there is several lines of other calculations, but what we want to find here is basically as in last week. What we want to find is basically the torque, or in this case the force that is produced inside the plunger. So if you want to isolate the force field here and isolate this, therefore bring out any other parameters to the other side and develop the equation without going into details, we will get the equation which is equal to the force field equals to I square over 2. So I square is the current that's circulating inside the winding over 2 multiplied by dl over dlx over dx. So what is dlx over dx? Dlx over dx is basically the variation of inductance L. So we know that we can calculate inductance because the relation of inductance is basically inductance is the flux linkage divided by I, right? So it is the difference of inductance over the variation of dx. So what it means is if we look at the position of the plunger, as we move the position of the plunger, the value of inductance L will change, right? We know because if we change X, what happened is the air gap, the reluctance change. If the reluctance change, therefore the flux change. So if we do flux multiplied by N, which is the flux linkage, divided by I to get inductance, the inductance will change. So with the position of X of the plunger, there will be different value of L, and that difference value of L multiplied by current square over 2, that is the thing, that is the part that produce the force. Okay, so if we can summarize the equation, we could say that in electrical machines, if we could summarize, the part that is create the torque or the force is basically what we call the variation of inductance. So the inductance L, if L is always constant throughout any position, let's say, so position, there is a position of between a moving part with regard to the static part. So the static part, we call it as stator in electrical machine. The moving part, we call it as rotor, for example. So here it is a plunger because it's a lateral movement. So as the moving part moves, if there is a variation of inductance as it moves, then there will be force or torque created between the two components. But if you move in any other direction but there is no variation of L inductance, then you will not create the force. So the force or the torque is created due to the variation of inductance. So in order to create a high amount of torque, you need to have a very high amount of inductance variation, dlx over dx. So here it's dlx over dx because the variation of reluctance is due to the variation of x. But later in electrical machine, in a rotating machine, of course it's going to be dl theta over d theta, because the moving part is basically it's a rotational movement, and in function of its move position, you will create that variation of inductance. Therefore, you will be able to create a certain force or certain torque. Okay. So here we are going to look at an example over here of creation. We're going to look at the calculation of torque that is produced in an elementary form of synchronous machine. So in previous exercise, when we use the Lorentz equation, Lorentz law method, we use an elementary form of DC machine. Here I'm taking an example of another type of machine, which is an AC machine, and it is what we call as a synchronous machine. Okay, so this two type of machine, we're going to look at them more in detail in the coming chapter after we have completed this basic principle of electromechanical energy conversion. So what do we have here? So we're going to read the question first. So the magnetic circuit here, it is a magnetic circuit, right? We have basically a conductor, and the conductor is basically a coil inside the what we call the component as a stator. So there is a current that is going into the stator here. So this is basically a cross section, and the machine is basically going inside the paper or the screen. And here we have a current that goes inside the screen, and it goes behind the machine, and then it comes back through this part, and the current comes out of the machine to goes into this negative terminal. So there is a current. We have a conductor here, and it continues to the bottom over here on the other side, and come back here and rejoin the negative terminal over here. So we have a coil. Basically, you can create a multiple round of coil around here. So it is let's imagine it's just one conductor for the moment. Okay, and then we have a core material in the stator, so we're going to call it as stator core. And then at the middle we have a shaft that is has a certain form. So if you look at the form, it is not a totally completely circle. It is an oval form, and the rotor is basically also made of the same material as the stator. It's just that it is mounted on a shaft, and it can be freely rotated inside the stator, right? So the magnetic circuit here consists of a single coil stator. So there is a single coil, as I mentioned just now, and an oval rotor. Because the air gap is non-uniform, so we have an air gap that is non-uniform, right? So if you look here, there is a rotor axis. In this direction of rotor axis, we can see that we have the larger radius of the oval. So the air gap over here is smaller, and here 90 degree to the rotor axis, we have basically the other direction where we have a maximum air gap, because here the radius of the rotor is at the smallest part. So we have the air gap over here. We can totally see, obviously see that the air gap over here is different. So if we account for the if we look at the magnetic circuit, if the flux have to go through the direction in rotor axis, the reactance will be small, therefore the flux will be higher. But if we have to go through this direction that is perpendicular to the rotor axis, then the air gap will be larger. Therefore, the reactance will be the reluctance. I'm sorry, not reactance. The reluctance will be larger, right, due to the much higher air gap. Therefore, the flux will be smaller. So there is a variation of flux. Therefore, variation of inductance, right? So if there is variation in inductance, then there is a possibility of a creation of torque inside the machine. If the rotor is uniform, completely circle, then we will not be able to create any torque. But here there is possibility of creating torque, even if the rotor here is just a piece of ferromagnetic material without any coil or without any permanent magnet. Okay, so the coil inductance varies with rotor angular position, as I mentioned just now, right? So there is a position where the inductance will be higher because the air gap is smaller. There is position where the inductance will be larger because there is a more air gap. And the inductance can be measured between the magnetic axis of the stator coil and the major axis of the rotor. And in the observation, as they measure, they get the equation or the variation of L theta. L theta in function of the angle theta. The inductance measured was equals to L naught plus L2 cosinus 2 theta, with L naught equals to 10.6 millihenry and L2 equals to 2.7 millihenry. So let me explain what this means. If I can have a pen. So let's imagine if we have an electrical machine like this, the first thing to start with, to get a bit of intuition, is of course to draw, to sketch your magnetic flux, right, or magnetic field line. So we can see that the current gets into the paper on this side and gets out of the paper on this side. So let's just try to sketch the direction of magnetic flux first, or magnetic field lines. So if the current, if you look into this part of the conductor, if the current goes inside the paper, you use therefore your right hand rules. It goes inside the paper, so you will have a magnetic flux around the conductor that goes in clockwise direction, right? So there's going to be a magnetic flux in this direction, and of course, because we have a ferromagnetic material over here, it won't go into the air, because the air has a higher permeability. So the magnetic flux tend to circulate in this direction, and it would want to go back to complete a circuit like this, following this direction, right? So it goes with a clockwise direction like this. And the same goes for the conductor at the bottom. So it's gonna go like this, and it goes in which direction? So this time the current goes out, so it goes in counterclockwise. So the magnetic flux is gonna look like this. Okay, so if you look at here, what happened is we have two magnetic flux that goes around the coil, and of course the flux, in order to get back the magnetic field line, in order to get back to close the circuit, they will have to cross the air gap. They will have to cross the air gap and get into the rotor. So it starts in the stator core. In order to close back the loop, they have to jump over the air gap and goes inside the rotor and jump back into the air gap to get back and close the circuit on both sides. So what happened here, we can see that there is a certain value of reluctance. I'm going to take another color. So there is a certain value of reluctance over here on the top side, and reluctance over here due to air gap on the bottom side as well. So as the rotor moves, so this is our rotor, right? So if we're supplying current to the inductor, means to the coil, as we move the rotor, we can move the rotor and we can measure the inductance. The inductance will be different in function of the position of the rotor, right? So imagine if I redraw it, imagine if we have the two conductor over here. If the I'm going to exaggerate the form of oval, of course. If the rotor is in this direction, then it will be very easy for the flux to go through the rotor, right? But if it is on the other direction, imagine if it is in this direction, then it will be much harder for the flux to go through the rotor. Why? Because in this direction, basically we can see that you will go through a lot more air gap in here. Instead, here you will go only through a small amount of air gap in the machine. I haven't drawn the stator, but if we have to draw the stator looks like this, right? So there is more amount, if you try to draw it properly, there will be larger amount of air gap when you are in this position compared to if you are in this position. So there is basically a preferred direction where you will have a maximum amount of inductance. So here you will have maximum amount of inductance. We're going to call it as L max. Here you're going to have a minimum of inductance. We're going to call it as L min. So L max and L min is basically these two L. L max is what they call as L naught, and L2 is what they call as L min. So if you look at the inductance, in this position, you have inductance of the highest inductance possible, which is equal to 10.6 millihenry, and L2 here, you have the smaller amount of inductance, which is 2.7 millihenry. Okay, and the variation in between both is given by this equation of L theta equals to L naught plus L2 cosinus 2 theta. Okay, so why cosinus 2 theta? Cosinus 2 theta because basically whether it is in 0 or 180 degree, you will fall over the same value of inductance, right? So that's why we have this 2 theta. So in between this position, this is the equation. And due to this variation of inductance, if we look at the equation previously where we have the torque created in electrical machine, what was the equation just now in previous slide? It is equals to I square divided by 2 multiplied by L theta. So dl theta over d theta. So if we have a variation of L theta, because L theta here is described by this equation, if you can write dl theta, so here of course we can find the derivative of this term. And here if we have cosinus, if we do the derivative, it's gonna be minus sinus, right? Then you will be able to find a certain production of torque inside the machine. So what is important is in this equation to note is that this machine will be able to create torque because we have a certain variation of inductance, and there is a position of maximum inductance and minimum of inductance, and in between usually it could be described by a certain equation like this. Okay, so an interesting point to note is that in practical condition, we usually try to find this equation by finding basically the maximum inductance L max and the minimum inductance L min. So how do we do this? If you have an electrical machine, you basically can find this L max and L min by two means. Is either to measure or to estimate by calculation. If you want to measure it, you can use an Lcr meter. So Lcr meter, this is an Lcr meter, an advanced one, which is pretty expensive. So basically, it uses just the principle of impedance in AC analysis. So it will inject a certain sine wave with a certain frequency and a certain small voltage, and it will estimate your value of inductance. So for example, here in this inductance meter, it shows a certain value of a very small inductance, 380 nanohenry. So this kind of instrumentation can be used. So you will have two probes, just like in multimeter. So this one is an expensive one. You could also have it in the form of like your multimeter, right? But it is an Lcr meter where you have two probes, two pens, and you just put your pens onto your two terminal of your inductor, of your winding, and then it will tell you what's the value of inductance. Or there is another method which is usually more precise by using the function generator and oscilloscope method. So there is a video that I put in the slide that you can look at it. So basically what we do is basically we do an AC analysis by injecting a certain sine wave, and we calculate basically the voltage at different frequency and using an AC analysis, because we know that in AC we will be able to calculate there is the Ohm law in AC, where Ohm law is as usual is the relation between voltage and current, but here you don't have just U equals to Ri. It's not R, it's impedance, and impedance now take into account the resistance of inductor and also the inductance of the inductor, which is in impedance is equal to JL omega. So by basically, if you look at the video, by injecting different level of voltage and different level of sine wave frequency, you will be able to determine basically the value of inductance. So if you have an electrical machine, you should what we do is, this is a very interesting test to do. Measure the inductance and then rotate the motor to look at the variation of the inductance across the rotation of the rotor, and therefore you will be able to estimate and calculate the possibility of the torque generated in function of the current. So it's basically is dl theta over d theta multiplied by the current injected divided by 2. So the torque is proportional, of course, to the current. If the current injected is higher, then you produce more torque, and also depending on dl theta over d theta. So I2 is depending on the current injected, but dl theta over d theta depends on what? On the magnetic circuit, therefore on the what we call as topology of the machine. So if you have a very oval form of rotor, such as in this example, then you would have higher difference of L0 and L2. So therefore this equation L0 and L2 will be much higher, difference of inductance higher, therefore possibility of creating more torques. But if you have other forms with different L0 and L2, therefore you will be able to create more or less torque in function of the topology or the architecture of your rotor. Okay, so let's try have a look at this particular equation over here, this particular example of machine. How do we calculate the torque? So as mentioned just now, we have the calculation. Basically, what happened? We have the machine, and someone takes the care to measure the inductor. We have the maximum inductance L0 equals to 10.6 millihenry, and the minimum inductance of L2 equals 2.7 millihenry. So there are two positions of maximum and minimum. We also call it, you might find in textbook, we'll talk about it later when we talk about AC machines. We might call L0 as direct inductance, and L2 as what we call as quadrature inductance. There are basically, they actually means maximum and minimum inductance. And the equation that describes their variation is this equation. So the question asks us to find the torque produced. So how do we find the torque produced? We know that we have the equation just now from the energy method, that the torque in function torque is of course varies in function of theta, equals to I square divided by 2 multiplied by dl theta divided by d theta. Therefore, you have to be able to find L theta first. So this is basically the plotting of the inductance. So the plotting of L theta. If you look at L theta, of course, as mentioned in the equation, is a cosinus waveform. Right? You have a maximum over here of a certain value, and you have a minimum over here with a certain value, and it has a certain average. So the inductance in Henry here basically changes and varies across time. So in order to calculate the torque, we will use the formula. What you need to do is just to basically calculate dl theta over d theta. So dl theta is basically the derivative term of L theta. So L theta just now is L0 plus L2 cosinus theta. So if you derive this, so L0, the derivative of L0 is constant. So if you derive L0, then you would have 0, right? And you have nothing. But if you derive dl theta of this term, L2 cosinus 2 theta, what you get is you'll get minus 2 L2 sinus 2 theta. So you have the torque in the form of sine wave, right? So this is the equation here, is basically is the equation of the torque. So we can see that the torque will have the form of sine wave in function of the position of theta. Okay, in function of position of theta. So the torque resembles to this curve, but instead of being a cosinus curve, it will be phase shifted by 90 degrees. So the curve, it is the same curve, but it will start over here, and the amplitude, of course, it will be multiplied by minus 2 L2, right? Minus 2 L2. So minus 2 L2 means there is a coefficient over here, and then it's also multiplied by I2 over 2. So it's going to be, if minus, then it will be starting at the bottom over here. Yes, at the bottom over here, and then it will follow this sine wave. It's just that the maximum and the minimum will be depending on this value, which is I square divided by 2 multiplied by, so minus, multiplied by 2L, right? So the amount of torque, maximum and minimum torque, will depending on I2 and L as well, L2 over here as well. So we can see that in function of the position theta, we could have either minimum torque or maximum torque. So if you want to have always a certain amount of torque, then you have to make sure that your rotor is always in the position of that theta. Okay, so if, for example, if we substitute with the value in the exercise, we are basically given with the value of L2, and then we are also given with the value of I. I'm not sure what was the value of I that was given, but if you replace with the value of I, you could get the equation that describe the torque. So for example, here, by replacing the value, they get the torque equals to minus 1.08. So the amplitude over here will be minus 1.08. multiply by 10 to the power minus 2 sinus 2 theta, so sinus, so this is the sine wave, but it will start at 0 over here. Okay, so note that in this case the torque act in such a direction as to pull the rotor, to pull the rotor. So if we look at the relation between the magnetic field over here and the equation over here, so it says that the torque is proportional to sine 2 theta. So if theta equals to 0, let's imagine, so theta equals to 0 when the rotor is in this position like this, then you will have the torque equals to 0, or the minimum torque, right? So when it is in this position, lateral, completely horizontal position, the rotor, then you have sinus 0 equals to 0, therefore you would have no torque at all. And then as the angle increase, if you are positioned at, for example, at 45 degree, when you are at 45 degree, then 2 theta becomes pi over 2, or 90 degrees. There you have the maximum torque. So it is like the position that we have over here. This is the position, basically you have the maximum torque. And as you increase the position into, for example, 45 degrees over here, 2 times 45, so 90 degrees. So if it is 90 degrees over here, then I'm sorry, if theta equals to 90 degrees, then 2 theta equals to 2 theta equals to 180. So 180 means we have back torques equal to 0. So if we have to point out the torques, when it is here, then we'll have a 0 torque. When we are here, we have 0 torque as well. When are over here, we have 0 torque. When we are over here, we have 0 torque. But in the middle over here, and in this quadrature over here, we will have the maximum torque point, right? Where we have maximum torque point. So what's happening is basically, if we look at what happened when we are at position like this at 0 degree, we have the flux line that goes in this direction, right? So it is in a completely stable position where it doesn't need to either move to the left or to the right. But as it moves in this direction, where it is positioned like this, then it will have the tendency to realign with the axis of the conductor, as mentioned previously in this node over here. But once it is aligned, then you will have no torque again. So of course, the position of no torque over here is what we call as the stable position. They would like to be aligned either horizontally or vertically. And in this position, therefore, it is the stable position where you have 0 torque. But if you start to get further and further from that both two positions, you will have higher and higher torque. And where else you could be to have the maximum torque is the position in between the two stable position. Therefore, it is at the 45 degree position in between the x-axis and y-axis. So that is the stable position of the axis. We call it as axis L, Q, and LD, right? So this is the maximum inductance, minimum inductance, and maximum inductance. So in this position, you have your rotor aligned with no torque, but in between, you will have basically the point where the torque will vary, will change, and there is a in between the position of maximum torque. So this method of calculation is very interesting because we could relate it directly with the position of the rotor inside our stator. So if you want to continuously have basically maximum torque, what happened is the magnetic field in the stator, where previously they were located here and here, we have to move them so that it will always be 45 degree in relation to the direction of the rotor. So that's what we're going to see later in the control or drive of synchronous or AC motor. We will have this parameter of what we call as load angle. So the angle between the magnetic field in the stator with the angle with the direction of the rotor. So that's all what we have to see this week. Overall, in conclusion, what we have seen is basically the most important thing that you have to recognize is that there is a method of calculation of torque that is using what we call as method of energy, and the formula is very simple. Formula is basically it's I squared divided by 2 multiplied by the variation of inductance over a certain position. So the torque is, if you write the equation, is I2 divided I squared divided by 2 dl theta over d theta, and therefore there is the relation between the position of the rotor that change the inductance. So we need to have this variation in order to create torque. So we'll be using one of these two methods. Usually this is the method that we're going to use, and of course, in order to use this method, you have to know the equation for L, the inductance variation of L theta over here. And we have seen just now how do you find L theta. To find L theta is basically you have to measure the inductance as the position of the rotor changes, and in order to do that, you could either measure it using an Lcr meter or use the method of oscilloscope and signal sine wave generator. Okay, so that's all for this week. Next week we're going to start to look at more specifically into DC motor, or what we call as electrical machine with commutator. So thank you. I'll see you in the next week video in week 5. Thank you.